Hello everyone, in the lecture today we will continue the introduction about the flexible pavement design with AI method. We will try to finish all the rest contents in this method. The thickness design for the pavement structure is the most important component of the AI method. For the thickness design, we have to use the MAT, the mean annual air temperature in the design area. And we need to use this information to select the thickness chart for the identification of the total pavement thickness. And this chart will be categorized based on the base thickness, the asphalt mix types, and the resilient modulus of the subgrade soils. Also, we need to have some input variables, including the designed ESAR, the resilient modulus of the subgrade soil, and the pre-selected materials. And the chart will actually provide the total pavement thickness. With the total pavement thickness, we can then utilize the minimum asphalt concrete thickness, usually is 2 to 5 inches, and then estimate the emulsified asphalt base thickness by subtracting the minimum asphalt concrete thickness from the total asphalt concrete thickness obtained from the chart. And we will show the details about how to do the design for the thickness for different layers and different pavement structures. In the AI method, we have to use MAT, the mean annual air temperature, for the selection of the chart to determine the thickness of the pavement structure. And this temperature is usually applied to check the freeze-frost effect applied to the pavement. And based on the value of the air temperature, the frost effect can be categorized into 3 types. If the temperature is less than 7 degrees, then we say that there must exist the freeze-frost effect. If the temperature is between 7 and 24 degrees, which we called 15.5 degrees, then it's possible to have the frost effect. If it's higher than 24 degrees, we will say that there does not exist any freeze-frost effect for the pavement. In this page, we have one chart to show the estimation about the thickness of the pavement structure for the deep strength pavement. Basically, for the deep strength pavement, we have the asphalt concrete surface, the asphalt concrete base, and the granule base. And behind the granule base is a subgrade. The chart will provide the thickness of the asphalt layers, including the surface and the base layers. This chart is actually applied for the deep strength pavement with 150 millimeter thickness of the granular base, and it's applied to the situation when the mean annual air temperature is less than 7 degrees, where we have to consider the frost effect. In order to identify the thickness of asphalt concrete layers, we have to know the resilient modulus of the subgrade MR and the designed ESAR for the pavement. With these 2 values, we can then identify the total thickness of asphalt concrete surface and base. For example, if the resilient modulus is 100 megapascal and the ESAR is set as 4 times 10 to the power of 5, then we can identify the thickness of the asphalt layer as 100 millimeters, which is actually the minimum thickness of the asphalt layer. and also it's the total thickness of the asphalt surface and the base layers. This page shows the chart for the estimation of the thickness for the deep strength asphalt pavement. Well, in this chart, we assume that the granule base have the thickness of 300 millimeters, and the air temperature is also less than 7 degrees. With the designed ESAL and the resilient modulus, we can then identify the minimum thickness of the asphalt layers. The chart here shows the estimation of the thickness for the full depth asphalt pavement. From the previous slides, we know that the full depth asphalt pavement does not have the granule base layer. Instead, it has the asphalt surface and a very high asphalt base layer. And behind that is a subgrade. The chart will show the total thickness of the asphalt surface and base layer. And it actually applied for the situation when the mean annual air temperature is less than 7 degrees. Also, we need to know the designed ESAL to the pavement and the resilient modulus for the subgrade. Similarly, if we consider the MR value of 100 megapascal and the ESAL as 5 times 10 to the power of 5, then we can get the thickness of the asphalt layers as 145 millimeters, which is the thickness that we selected between 125 and 150. And this thickness is applied for both surface and base layers. And the chart in this page shows the thickness with respect to different ESAL and resilient modulus for the deep strength asphalt pavement. And the thickness of the granule base is set as 150 millimeters. Also, the mean annual air temperature is between 7 and 24 degrees, which is 15.5 degrees. By using the ESAL and the MR of the subgrade, we can find out the thickness of the asphalt layers, including surface and base asphalt layers. The chart here is applied for the deep strength asphalt pavement, where the thickness of the granule base is set as 300 millimeters and the air temperature is set as 15.5 degrees. And this chart is applied for the estimation of the asphalt layer thickness for the full depth asphalt pavement. The mean annual air temperature is set as 15.5 degrees. Similarly, we have to use the ESAL and the MR of the subgrade to find out the thickness, actually the minimum thickness of the asphalt layers. Moreover, if the mean annual air temperature is higher than 24 degrees, where we don't need to think about the frost effect, then we can use the chart here for the estimation of the thickness of the asphalt layers for the deep strength asphalt pavement. And this chart is applied for the pavement which the granular base has the thickness of 150 millimeters. Similarly, this chart is applied for the deep strands asphalt pavement with the thickness of the granular base as 300 millimeters and the mean annual air temperature higher than 24 degrees. And at last, we have the chart to estimate the thickness of the pavement layers for the full depth asphalt pavement under the situation of the mean annual air temperature higher than 24 degrees. You also need to use ESAR of the pavement and MR of the subgrade to find out the minimum thickness of the asphalt layers. Also, there are some recommendations about the thickness design based on the field observations. First of all, if the quality of the subbase is weak, then we should place a minimum of 150 mm or 6 inches of the base course over the subbase. If there is a severe frost effect, then we have to consider using 300 mm or 12 inches of the base course to minimize the frost action. In addition, sometimes we will increase the thickness of the base layer, but it's not recommended to reduce the asphalt concrete thickness based on the increased base thickness. We will still need to apply the designed minimum asphalt concrete thickness based on the charts. There are also some recommendations about the full depth asphalt pavement. Basically, the thickness design for the full depth asphalt pavement shall be related to the traffic loadings. For the parking lot, driveways, or rural roads with the ESAR less than 10,000, the minimum thickness of the asphalt concrete wearing course, which is the surface layer, should be higher than 25 millimeters. For the median truck traffic, where the ESAR is between 10,000 and 1 million, the minimum thickness of the surface layer should be 40 millimeters. For the road with heavy truck traffic, which means the ESAR is higher than 1 million, then the minimum thickness should be 50 millimeters. Similarly, there are some recommendations for the deep strength asphalt pavement. Based on the traffic loadings applied to the pavement, there are some requirements about the minimum thickness of the asphalt concrete layer, which is the asphalt concrete base layer for the deep strength asphalt pavement. When the ESAR is less than 10,000, the minimum thickness is 25 millimeters. When the ESAR is between 10,000 and 1 million, the minimum thickness is 100 millimeters. And when the truck traffic is very high, more than 1 million, then we should have the minimum thickness of 125 millimeters. We can also apply the simplified AI design approach to determine the pavement structure, including the thickness of the pavement layers for some specific road types, including the residential driveway, parking lot, and truck unloading area. And the design could be applied for full depth asphalt pavement and the deep strength asphalt pavement. Also in the design, we have to consider the impact of the subgrade soil. We need to consider the quality of the subgrade soil, and usually is categorized into 3 types: excellent and good quality of the soil, fair quality, and poor quality. For the full depth asphalt pavement, if the subgrade soil is excellent, then for the residential driveway parking lot, the thickness of the asphalt layer for the full depth asphalt pavement is all 100 millimeters. But if the quality of the subgrade soil is low, then we have to increase the thickness of the asphalt layers. Moreover, usually for the truck unloading area, we have to set a much thicker asphalt layers. Similarly, for the deep strength pavement, we have some recommendations about the crushed aggregate base with asphalt varying coarse thickness, which would be the aggregate surface course and the emulsified aggregate base layer. With that, we can find out the thickness of the both layers for different types of the road. While similarly for the residential driveway parking lot, the thickness will be much smaller, and we have to put a much higher thickness about the both asphalt layers and the aggregate layers. Now let's see one example for the implementation of the AI method for the design of the flexible pavement. And the pavement will be designed for a two-lane highway. And we are provided with the information of the traffic and the subgrade soil. We know the initial annual average daily traffic is 2,000, and the annual traffic growth rate is 4%. And this pavement is designed for 20 years. We also obtained the CBR test data, and we found that there are some possible freeze-thaw effect, which means that we have to consider MAAT as 15.5 degree. And we're going to use this information for the design of the pavement thickness. Also, we are provided with the truck traffic on the designed lane for each direction, which is shown in the second column of this table. So this is also the input information provided by the example. And then we can use this information to calculate the total ESAR for the designed lane. The table here shows the truck traffic for different class of the trucks, and the total daily truck traffic for the design lane is 100, and we can then find out the annual truck traffic for the design lane by using the column 2 times 365 days, which will be the annual traffic. In addition, based on the annual growth rate of 4% and the design year of 20, we can find out the growth factor as 29.79 for the whole design period. With that, we can find the lifetime truck traffic as the product of column 3 and column 4. So that's the lifetime truck traffic. In the previous lecture, you can find out the table to identify the truck factor, which is a TF. For each type of the truck class, there's one specific truck factor. And the ESAR will be the product of the lifetime truck traffic and the truck factor, which will be the ESAR of each truck class as shown in the column 7. And then by summing all the truck traffic for different classes, we can find out the total ESAR for the designed pavement. We also conducted the CBR test at 8 different sections in the pavement, and used the equation MR equal to 10.342 times CBR to estimate the value of the resilient modulus. And the result is shown in the first column here. With this information, we want to find out the 60, 75, and 87.5 percentiles of the resilient modulus. To do that, we first need to sort the test value from high too low. And then identify the percentage for each value, which is shown in the fourth column in this page. With that, we can plot the sorted test resilient modulus and find out the 3 different percentiles. For the 60 percentile in this figure, the value is 67 megapascal. For 75 percentile, the value is 60 megapascal. Also, we can find out the 87.5 percentile as 53 megapascal. Now we can go to calculate the pavement thickness from the design charts. From the previous analysis, we know that the ESAL for the design period is 431,455, which is actually between 10,000 and 1 million. In this range, we have to choose the resilient modulus at 75 percentile. And then with the figure in the previous page, we found that the 75 percentile of MR is 60 megapascal. Then we can use the information of ESAL, the value of MR, and the selected mean annual air temperature MAAT as 15.5 degree to select the appropriate design charts. We want to find out the pavement thickness for the full depth asphalt pavement and the deep strength asphalt pavement. Actually, here we will only consider the deep strength asphalt pavements with the thickness of the granule base as 150 millimeters. From the design chart, we can find the thickness of the asphalt layer for the full depth asphalt pavement as 185 millimeters. For the deep strength, it's 150 millimeters. In the next 2 pages, we will show how to find out these two thickness. This chart is applied for us to identify the thickness of the asphalt layers for the full depth asphalt pavement. We know the resilient modulus is 60 megapascal, which is the value here, and the ESAL is 431,000, which is some value here. With these two values, we can find out the thickness is around 185 millimeters based on the linear interpolation from 175 to 200. Also, here you should pay attention about the chart, which will be applied for the full depth asphalt pavement and air temperature of 15.5 degree. Similarly, for the deep strength pavement, we have to consider the thickness of the granule base as 150 millimeters and MAT at 15.5 degree. With this chart, we can identify the thickness of the asphalt layers based on the MR value of 60 megapascal and the value of ESAL as 430,000. So we can get the thickness as 150 millimeters. In the flexible pavement, the top-down cracking is also very common. However, the mechanism of the top-down cracking is not well understood yet, and it's not considered in the current asphalt design procedures. So in this class, we will not consider the top-down cracking criterion in the AI method and the following asphalt method. While for the long-life asphalt pavement, the impact of the top-down cracking should be considered. So that's all about the lecture today. Thank you very much for your attention. With that, we have finished all the contents about the AI methods. In the next lecture, we will introduce the asphalt method for the design of the flexible pavement.